Hello and welcome to tutorial 6 of Let's Learn C for Beginners. So in this video we are back onto the desktop again. So three things I wanted to go through in this video. So command line arguments, what they are, how to use them. I'll then go into the Var Args. I guess it's a structure. It's basically a way of passing variable amounts of arguments to functions. And then I'll go into memory management and literally go through how the C compiler organizes the memory of a program and how it's affected by the operating system also, as the operating system has to allocate some space for our programs as well. And then I'll go over how we can create memory dynamically for various uses. And for our variable arguments function, I will give you a useful example to use of the CString structure. And then I will do another one for the memory management one as well, where I will provide an array list object as well. So first off, what I'll do is I will go into the first program now. So I'll show you it running in Windows first. So what I'll do is I'll open up. So here we have basically an empty program in the Windows code block project here. So what I'll do is, in fact, I don't want to do that one first. It is the command line one. So if I zoom in here first, I will comment out using C strings at the start here, and I will concentrate on the variable arguments. So basically, when a program starts up, the operating system passes a number of arguments to the program, and it passes two variables as such. We have argc, which is the amount of arguments which have been passed on the command line. So the amount of things you can pass on the command line varies. So if you've ever sort of run like a program from the console here, the command prompt, usually you might type in the program's name and then you pass a number of different arguments to it. And all of the different arguments, they are all actually stored as separate strings. So what this here is it's a string array, basically a C string array. So if what this program here will do is, using argc, it will loop over all of the strings in this string array here and print them out for you to see. So if I build this program first, so if we run it first off, what it will show you here is it will show you the path. So argument 0 is always the path to your exe. So an easy way to figure out where your program is actually located is to get argument 0. And then if you remove your program name up to the slash here, then you actually have the path where everything is stored in your program. So if someone runs your program on a different computer, obviously they might put it in whatever folder and whatever sort of path which is convenient for them. So if you have various files which you need in the same folder as your exe, then you need to know the path to be able to load them. So obviously this is all well and good here, but now we need to figure out where that is. So that program there is located in here in my documents here. So if you go to the bin file in the release, so this is the exe file here. So if you copy this path here and navigate to that directory. So ls basically lists everything in there. So if we do test.exe and then we say hello 45 100 1025 and then press return, this is the program running here, and this is what it's got here. So the first thing that it actually shows you here is the path, or rather the name of your program here. So if you run this in an actual command prompt itself, then it just gives you the actual local name, and then you can see here that so there's 4 arguments in the command line, and this is them all here. So they've all been passed to the our program here, and then using the different, if I just get back out of this a minute, back to here. So this is a useful way to get arguments into your program. So if you were creating, for example, a graphics converter or some other like tool application, like I've got many different graphics converters for the different consoles. Most of the time the easiest way to sort of create them is via the sort of command line or the terminal window, where a user basically passes across the file name to convert and then various other parameters that you might need. So this is how you would get them across, and then you basically need to copy the various strings out of the argv array here. So now that I've shown you this running in Windows, I will now jump back to Linux, as everything there is exactly the same. This is just so that you can see the difference here if you are primarily interested in Windows. But yeah, everything pretty much is the exact same anyway. So I'll now open that program back up in Linux Mint here and show you the exact same again. And then I will also go over the Var Args. So I will do the same again. I will comment out all of this. Zoom in here. And then if we run that there, unfortunately I can't zoom in here. So what this is given us is exactly the same as in Windows here. This is the path directory here. So obviously, as this is Linux, everything is from my home folder here, not the C drive. And then if I navigate to the c++.com reference here, and then if you go to the, let's see, which one is it? Is it this one? Yes, here we go. So working with the command line, these functions here will be very useful to you. So you can convert this one here, converts a string to a double. So for example, if you're passing various numbers across, say the width of an image and the height of an image, then you'll most likely want to use the atoi function here to convert the string to an integer. Or maybe you want to convert it to a long or a float. So these are also some ones that could be useful for you when passing parameters on the command line. I'll come back to, well, in fact, while we're here, I may as well jump into the Var Args thing here. So if we go to the standard argument header here, this basically goes over the variable arguments handling, which is what the Var Args abbreviation basically stands for. And as it says here, the variable arguments handler basically allows you, when you create functions, to include one of the parameters as 3 dots here, just like it's showing here. And then what this allows you to do then is you can pass any number of arguments, and then using the variable arguments list type here, we are then able to extract those items from this list and then basically add them to an array or add them to a string. So I will show you a use for it here. So to use it, you need to include the standard arg header file here. So what I've created here is a more useful way of handling strings rather than a const char pointer. So what we have here is we have a char array called data, which will be used to hold our letters, and then we have an unsigned int here to hold the length of our string. And then these functions here allow us to basically, if you are familiar with other programming languages, then for example Java, C++ or C#, those object-oriented languages obviously allow you to create classes, and classes basically allow you to work on the sort of, you basically, it's a way of connecting functions which work on your data with the data. Basically, all a class is it's a struct which contains functions within it. We could easily fake that in C here. All you would do is you would have void functions with as like function pointers. But anyway, the way to sort of do this in C is basically you have your struct which contains the core data, and then what you do is you basically have the name, or this is the way that I do it anyway. So you have the qualifying name and then put an underscore, and then you have the function part. It's basically, if you were doing this in C++, you would sort of have CString, and then you would have new or something like that. That's how C++ kind of does it. In Java, you would have the well, I won't bother going over it here. This is the way to do it in the easiest way to sort of have like a clear object-oriented kind of way in C, where you include the name of your object, which usually I would have it match the struct. So then we have new here. So what this does is you pass in a const char array here, and then you include the Var Args 3 dots here. This just basically tells the compiler that there will be a variable amount of arguments to take after this. This is basically how printf and the various print functions operate. They all sort of rely on Var Args in the background to be able to populate their various additional parameters that you can pass. So I'll show you that here. So if I zoom in here a moment. So this is our new function here. So we have basically an empty string ready to use inside the new function here. Here we have our VA list, which we define. And then the way you kind of use this is you pass the argument, the VA list start, and you pass it the parameter to kind of start after. So you could do this with integers here and basically copy them out into an array of ints. And then basically what this says here with VA start is after this variable is where the VA list basically lives in the function, and then this vsnprintf function here is how we copy into the char array here using the message string here and the args here. So what this does, instead of sending as printf obviously sends a const char to the terminal or the console window, vsnprint, what this does is it sends a formatted string to an array. So if I come in here and open this up, where are we? And then if we come down here, you'll see that there's a number of different vsprint commands here. And then it basically gives you an indicator here of what the differences are. So we're using vsnprint here as it creates formatted data, and it takes in an argument list, and we basically specify a maximum size that the array will be for the data to be copied in. So this is more clear here. So the first parameter is a char array here. You then pass in how big this array is so that you don't overrun it by sending it too many characters. You then pass in a const char array. Basically, this is the string where the formatted text is, and then finally you pass it the VA list. And then what this does is it will go through the string you've passed in, and then where it finds the formatting symbols which are in printf. So for example, the %s or the \n or the %d, these symbols obviously substitute numbers at the end here of a normal sort of printf command. So this basically allows us to pass in all of these different arguments, if you like, which will then get put into a print statement or string, and then that then gets copied to the array. So this is basically what's happening here. This is exactly the same as the string code here. So if I uncomment that, so you'll see here, here's our string here, and then we can basically pass in variable arguments at the end here. So what's happening here is this is our string is this here. Whatever we pass after the string here is going to be put in the variable arguments list, and then the vsnprint function here, it's going to use the string we pass in and the arguments list with the numbers, and then it's going to go through our string here. Wherever it finds the special symbols, it will then substitute them for the numbers like a normal printf would do. The only difference is this string will live inside the array here. So it's an easy way for us to handle the strings ourselves. And basically it lays the way for us to handle printing ourselves. So for example, if we were creating a desktop game, obviously we won't be writing stuff to the a console window. We would be having to draw sprites, or maybe if we had like 3D text, we would be substituting each letter for maybe a 3D shape or something like that. So we would need to know the text and the numbers ourselves. And then after you've finished with the VA list, you have to call VA end with VList. The start and the end bit here, it kind of, I guess it kind of creates like a loop where it goes over all of the arguments. And then when this program runs, it's passing every argument to the vsnprintf function here. And then finally, we use string length to get the length of our string, and then we record that in the length parameter of our string type here. This then allows us to I've obviously only added a few functions here which I thought would be useful. Again, you can do all sorts of stuff now. So for example, maybe you want to convert your string to all uppercase or all lowercase, or you could maybe reverse your string, or get just the leftmost sentence, or maybe the rightmost sentence. Now that you have your string inside the data array here, you can basically do whatever you want with it. And obviously just add a new function to the CString here. So the other functions I've added here. So the add function here, this will basically allow you to add another formatted string onto the end of your current string here. There's also a clear function here where it will basically go through and zero out every element and then set the length of your string to 0 here. And then you'll see the add function here. What we have in here is we have a temporary sort of or rather we have a private string array in here for when we need to operate on additional strings passed into the functions here. For example, in this one here, what we're actually doing is we are copying the formatted string to our temporary string buffer. We then use a local variable in here to get the length of that string. We then work out how much space we have left in the string that we've passed in here. And then what we do is we, using this char pointer here, we get a pointer to the char after the current contents of the passed in string. And then we basically copy either the length of this new string here, or we copy the remaining space and fill it with the chars from this string here. This other function here, add other, basically does the same as the above, where it copies, except you pass both strings in by pointer here, and then it copies the contents of one into the other. And then we have another function here where instead of having to use printf, we can basically wrap it inside this function here and then pass in a boolean here to start new line. And then if I uncomment these here, So you see what we're doing here is we're passing in a number of different parameters to message 1. What I'll do is I'll comment out this moment and then we'll run that here. Wait a minute, I've not printed out. So what we'll do is we'll print this out first. So we pass that one by pointer there, and then we will add a new line there as well. And there you go, you'll see our hello world there, and then number 64 and 24.5. And then I will also show you the rest of this here before we move on. Obviously I will include these programs so you can have a play around with the CString structure. I basically use CString everywhere, whether I'm coding on the NES or the Wii or the desktop. The CString is a valuable object. So all I've done here is basically using the add function here to pass in another string to message 2 here. So basically gone through to demonstrate the way that the add function works here, where you basically make sure that the string doesn't overrun. So one thing with C strings as well to be aware of is they are what's called null terminated strings. That means there is a hidden char with the value of 0 at the end of each string. That is what tells printf and the various printf functions when it has reached the end of a string. There is a 0 at the end. So loads of times what you'll do is you always make sure that at the end of your string you add a 0, just to make sure that it's not going to be overrun, basically. Which is why you'll see here I've added an extra 1 at the end of our C string size here, and that's to basically set aside one char for the null terminated value. So another way of doing that is to I think it's that one there, which is the same as that there, 0 basically. So hopefully that's made sense to you there, and this is a useful example of C strings there. So for example, it allows you to it is as easy as that. obviously the whole idea of doing all this, where you basically wrap printf in here, is obviously if you're working with a load of different text over and over again, you obviously don't want to be using printf all the time. And obviously if you were working on a desktop GUI application or something that actually creates a window, then obviously you can just substitute printf for a command to actually draw graphics onto the screen. So that's the example here of using variable arguments and the Var Args object and the various VA list parts. So what I'll jump into now is working with memory. So what I'll describe is basically how these programs basically work, where the C compiler, obviously you pass in your C code here, it then organizes it all into a way that the CPU can actually work with. So if I jump back to here, so let's go over how these things work. So if you saw the other videos on the Commodore 64, you would have seen me creating a linker program where I was basically going over how the linker for VBC C6502 should organize the memory layout of the programs. And in there you will have seen there was some of these being battered around, these terminologies, BSS data.txt. And that's something that is common across all of the C compilers. They all have these sections in them. The linker obviously has to take your program and then sort of create a kind of container, and inside of that container organize everything in a logical manner for the program to be executed on the computer itself. So to note here, there's three main types of storage that our program variables use in C. We have the stack, the heap, and the data region. So you'll see here, this is like a virtual container here, where at the start of our program you'll see the command line arguments and also some details about the actual environment it's running on might be contained in the program container. Then you have what's called the stack. This is where local variables and function parameters are stored temporarily. Also, if you think of like for loops, where you create like a temporary iterator, that's also stored in there as well. The idea is they are temporary, so these variables are pushed on the stack. Once they've finished being used and the program moves on, they are then discarded and the stack would shrink. There's then another memory area called the heap. So one thing to note is the CPU organizes the stack. It's not anything that we actually can control ourselves. It's all done automatically, whereas the heap is basically a bucket of memory which we have to request if we want to use it. So it's basically a dynamic area of memory where we ask the CPU to mark out and give us a region of memory for whatever use we decide. However, once we've finished with that, we must then inform the CPU and the operating system that we no longer want it and to release it. If you don't release it, then that's what's called a memory leak. If you've had your PC crash because of dodgy programs in the past, that's usually because they are allocating large areas of memory and they are not giving it back fully to the operating system. So eventually the operating system will run out of usable memory and then your computer will crash, or you'll have unforeseen things happening. And then there's also the data area here. So if you define like constant variables or static variables, then that's where they are sort of placed, and they live for the duration of the program. Again, they basically are handled by the CPU. Nothing for us to worry about there. And then yeah, that's basically how these things operate here. So another thing to note here as well is these program containers, if you like, are pointers, are basically working with virtual memory. The programs themselves are in what's called a virtual memory space. What that means is the operating system gives your program a virtual container of memory, and that memory region is specifically for your program only. So your pointers cannot interfere with the global memory on the computer that the operating system is looking after. Instead, you can only access memory within your virtual memory block. You'll see here in this example here, this basically we have two programs in memory. They each have a virtual memory window or container, and then you'll see here the .text, data, heap and stack areas, and this basically says where what's actually in them. So in a text segment, that's where your code actually lives. The data segment is the static and global variables. The BSS segment, this one here, is uninitialized static and global variables, and the heap is a dynamically allocated memory, and then the stack is for local variables and function call frames, basically the iterator variables and the loops, if you like. So I thought I would explain all of this before we move on to using the heap. So you'll see here the operating system handles all the memory on modern computers. On modern computers, we don't work with the real RAM addresses. We only sort of have virtual memory. The stack is handled by the CPU and is the default location for all of our local variables. And then another thing to note here is the different sizes, typical stack sizes apparently allocated by operating system. So apparently on Linux, the typical stack size is 8 megabytes apparently. And then Windows is typically 1 to 2 megabytes. It says per thread. I'm guessing that also applies to programs. And then Mac OS, 8 megabytes apparently. This is stuff that I've sort of seen online about this. I've not sort of played around with my own programs. It's not something I tend to worry about on the desktop. I kind of don't really worry about memory as much. Whereas when you are working on 16-bit computers and below, you generally don't use Malloc or the memory allocation stuff. You kind of need an understanding of the memory map of the machine you're working on. So the heap here, this is basically dynamically allocated memory, sort of like a memory pool inside the program space, as the pictures above showed. And then you, as the programmer, are responsible for creating this pool of memory by asking the operating system for it. And that also means that you need to pass it back when you're done with it as well, as the operating system is relying on you to handle the life cycle of that memory. And then the way that C allows us to allocate memory is it gives us 3 commands here. We have Malloc for allocating X amount of bytes. We have Calloc, which is clear and allocate X amount of bytes. So what Malloc does is it just chucks you an area of memory. It doesn't do anything to it. So the contents of it could contain anything, basically. So if when you went to work with it, you need to sort of make sure you clear the current contents. Whereas the calloc command here, this clears and allocates X amount of bytes. And then realloc will reallocate X amount of bytes from an existing allocation here. So if you think of you had like a small pool or a little bucket of water, and you now realize you need a larger bucket of water, what you would do is you would basically tip the water in your small bucket into your now larger bucket. You wouldn't throw the bucket away as such. So what realloc does is, if you grow the or if you decide you need a larger array of bytes now, then it allows you to basically grow the current area you have. And then what will happen is the operating system will either give you, or it will either extend the amount of bytes you have in your current memory block, or it will create a new large memory block, copy the current contents of your current block into it, and then pass you the pointer back. And then each command will return a void pointer if successful. Otherwise, it will contain a null pointer. So that means after each allocation or request, it is up to you to check whether you have a valid pointer or not. If you don't have a valid pointer, then whatever operations you do next on that pointer will be overwriting memory used for something else, which you aren't guaranteed will be free for you to use. So if I come back to the C reference here, and then you'll see these are in standard lib here. And these are the dynamic memory management functions here. So it says what they are for here on the description here. So this allocates and 0 initializes an array. And then each of these allocation functions relies on free at the end to pass it back to the operating system. And all you do is you basically pass your pointer to the free command, and then it will tell the operating system to release that memory. So here's an example here using the different memory allocations here. So this has got free. At the start here, these are free int pointers which point to nothing. And then you'll see here that the first one calls Malloc, and you basically need to pass in the size of the memory you want in bytes. So that's where the size of operator comes in use here. So you'll see here that this one's allocating 100 size of int. So that's basically 400 bytes, as an int is typically a 32-bit number which takes 4 bytes on modern computers, that is. And then you'll see here that the pointer is being cast to an int pointer here. And then you'll see Calloc is slightly different here, as in you pass in how many items you want, and then separately you pass in the memory footprint, or how big each item should be in bytes. And then what Calloc will do is it will obviously initialize each of those items in your array to 0. And then if you wanted to grow either of these arrays which have been created with Malloc or Calloc, you can use Realloc to basically resize that array here. One thing to note though is you shouldn't pass in the same pointer to Realloc. So you shouldn't have buffer2 equals Realloc buffer2, because if Realloc fails, then it won't actually destroy the contents of the array in memory. It won't release that block back. It will just tell you that it failed to resize it. So if you had buffer2 at the start here, it would return a null pointer, and then buffer2, you would then have lost the pointer, so you wouldn't be able to then free it, so you would cause a memory leak again. And then you'll see after this, obviously buffer2 is no longer in use after here. So only buffers 1 and 3 are then free back to the operating system, because buffer2 was basically resized by another 500 ints. So at the end here, buffer2 obviously doesn't exist. That's then a null pointer, and the address of that block is passed back into buffer3. So if you want to check out the other memory allocation functions here, this basically this is where you get them. So check them out here. So Calloc here, basically, there you go. That's the amount of the items, and then that's the size in bytes. And then there's an operation of using it there. So another one that's also useful when you're working with memory as well is the string h header file here, as this has various commands for copying and zeroing blocks of memory. Again, this operates in bytes. So memory copy here, you pass in the destination address basically. You pass in the source address and then the size in bytes that you want to copy, and then it will then copy the bytes from the source to the destination for you. And then here's an example of it here, basically working on strings here. So you could use memcopy to work with strings of text. However, there is no point doing that, as there are dedicated string commands to do that, like string copy. And another useful one I use all the time as well is memset, where you can basically fill an area of memory with a value. Which is what it's doing here. One thing to note with memset is obviously it's going to fill that memory with bytes. So really, it's only useful if you want to zero out something, or if you are working with bytes. If you were working with like ints, and you wanted to fill an area of ints, you would have to sort of create your own function to do that. So that's the memory allocation stuff for you there. And then, yeah, like I said here, once you've finished with everything, make sure you call free to release the command back to, sorry, you release the memory back to the operating system. So I will now show you an example here. So in this example here, I've created an array list of ints. So similar to what I was doing with the CString here, where I've basically gone down the object-orientated sort of way of doing things in C here. So you could easily change this. Say you wanted a float array, for example. There you go. Or you could have a byte array, for example. And then just duplicate the functions. So you'll see we have a new function, a destroy function for when you are finished with your array list, and then an add to add in one int, and then we have an add array of ints, where you basically say how many items are in your array, and then you pass a const int pointer to your array, And then we have a get and a set function here. And then the get function here will return an int, whereas the set function obviously takes in, you pass in the offset into your list, basically which item number in your list to change, and then you pass in your new int there. And then one thing I do at the in the header file here is we say, okay, so when we call the new function, what is our default size at the start? And then you basically have to decide, okay, when the array list needs to grow, how many items should it grow by? So this pattern is basically the same for every type of array list here that you can think of. So for example, say we had a game actor here, and then we had its X position, its Y position, maybe it's got a name as well, and then maybe it's got health as well. So you could easily substitute that for an actor there. So this here could either be a normal data type, or it could be a struct here. One thing you would have to do though is you would have to do a define here. And then you would have to make sure that you have an indicator for the size of your structure there. So I'll just build that a moment. So this is failed there, but that's because of the actor there. Oh, it's because I put it in there. There we go. So I'll change that back. So that's how you would basically have an array list for everything. So the commands you give for your array list is obviously, you could have all sorts of stuff here. So for example, you could have pop to remove an item, and then just as with the CString there, you just pass in your array list at the start. So let's get into the core code here. So I'm using Calloc here. So you see here we have our default size. So there's our default size there. And then we have our item size. So in this case, it's the size of an int here. So at the start here, we pass in our new array list. First, we set the capacity and the size to 0. So I'll explain what these are here. The capacity is the size of the array itself. That is the limits that you've allocated. So you call Calloc, Malloc or Realloc, and you the size you specify. The capacity is what's put in capacity. Size is how many items you yourself have put into your array. So if you had the pop function, for example, all you would need to do there is just to decrement the size of the array by 1. That's all you would need to do to basically pop off the an item. It is that simple with the pop command. If you wanted that sort of functionality, so you could easily turn your array list into maybe a stack, or you could easily have like a function to basically reverse the order of the items in your array list. You have the size variable there. So all that happens here is we call Calloc with the size of our array that we need to be allocated on the heap. We then cast the void pointer to an int pointer, which we store in our data pointer. We then check to make sure that the data pointer is not null, which is what this does here. And then if we have a valid pointer, we then set the capacity to the default size, and then we return true. So at this point here, our array list has been allocated with our default of 100 ints. However, its size is 0 as we have not added anything into it. And then you'll see here in the destroy function here, we first check that the capacity is greater than 0. So we make sure we're not calling free on a null pointer. I can't remember whether it says something about that in here, about the calling free on null pointers or not. Let's double check. Okay, so it doesn't matter. If the pointer is null, then it does nothing. This is the thing here, though, I guess. So if the memory basically, or the variable contains some spurious number for whatever reason, then you still could have an issue there. So it's probably always best to check that the capacity is greater than 0. And then what we do then is we call free on our int array, and then we set the capacity and size to 0. And that cleans up the memory we've allocated. So you'll see there that it's not really that bad working with pointers. The only sort of problem that you have is if an error occurs in your program. So normally what happens is if an unknown or a random error occurs in your program, then you'd obviously need to bail from your program as soon as possible. So loads of memory leaks occur when the winding down of all allocated resources fails. So if your program basically suddenly crashed for whatever reason due to an unknown or unseen error occurring, then any array that you'd allocated would potentially cause a memory leak. So let's go over some of these functions now. So what the add int function does here is we check to make sure the size is less than the capacity, and if it is, then we basically get a free int, assign the passed in value to that free int, and then we increment the size variable to indicate that our array list size has grown, and then we return true. We also have a kind of have some mini sort of error handling in here. However, in like large programs, you would need to have a kind of global way that every function in your application, if it finds an error, it then is able to signal to some sort of controlling variable that an error has been found, and then you would need to try and wind everything down, or to at least kind of alert the user that an error has occurred or something of that nature. Normally everything I sort of do is with print commands at the at various key junctions, if you like, to indicate to myself when I'm building these things that an error has occurred. Normally what would happen with your programs is you would bug test them a number of times to make sure that each different avenue that the program can go down has been tested and that there are no bugs before you sort of passed it to everyone to use. So you'll see here we basically check to make sure we have a capacity greater than 0. If the capacity equals 0, then this obviously means you've passed in an empty array list. So we basically print out a command and return false here. This would be sort of like shallow error handling, where you return false and take no action here, and then the user of the array list would then be expected to be checking that every time they added, they were verifying that the no false was returned, basically. Now, if size is equal to capacity, when we call add here, you'll see here the new size variable here takes in the current capacity of the array. And then if we get to this point, what happens is in fact, this is not right here. It should be grow size times int size here. So what happens here is the new size basically gets the grow size times the size of an int added to it here. This will be the new capacity. And then we have a temporary array int list here. We could just have an int pointer in here. However, if you sort of change this into an array list for something else, then you don't need to change the int pointer in here. So you'll see here our temp array list here. The pointer is used with realloc, where we pass in our array list data and our new size here. So as I was saying before, when you call realloc, you should have like a temporary pointer which will hold the return value from realloc. So if you have a valid pointer, that means that your data allocation has worked. And then you'll see here we basically copy the pointer from the temp array list here and set it to our array that we passed in. We then add the int grow list size to our capacity here. We then take a pointer to the starting point again, and then we basically do the same as we did here. We set the current position in the array, as in use size, to the new variable here. We then increment the size and return true. If for whatever reason this pointer returned was null, then we print out an error here and return false. And then in this one here, this basically allows us to add a new array into our array list instead of an individual. And then we basically inside a do while loop here, we copy each item from the passed in int array into our current array using the int add internally in here. And then in here, this shows you how we use the get function to return an int. We could just do this externally. So for example, because this is C, we can always do mylist could always do something like that directly. However, you would need to know beforehand what you were doing was safe. So the advantage that the get and set functions have is they have some basic error checking inside them. As you'll see here, this basically checks to make sure that the array list is valid. It then does a check to make sure that the offset you want to get, in this case, is smaller than the array size. If it's not, then it bungs an error back to you saying you're trying to access an item outside the limits of your array list. And you'll see we have the two same checks inside the set function as well to make sure you're not trying to set an offset which is illegal in your array list. So I think that is everything here. So I'll just go through the demo here. So the demo itself is not very exciting, just like the CString demo here, but the actual principle that I've put across in each of them is to provide you with something that's actually useful and to give you a real world use for explaining the Var Args, the command line arguments, and here using Malloc, Realloc and Calloc to dynamically allocate as much memory as you need for whatever task you need that memory for. So you'll see here what's happened. We're just adding in various numbers here between 0 and 300, as you see here. And then at certain points we basically output what the capacity is and what the size is. And then here I'm basically adding in these items here from this array in here. So you see we add an int there, and then this will get the value here, and then here we add in our temporary array at the top here. And then finally, once you're done, make sure you call destroy to free up that memory block and pass it back to the operating system. Right, that is it for this video. Hopefully it has been useful to you and I have explained things clearly so you can go forward and use the things I have talked about in this video. In the next video, I will go over how to create files, and I will also we'll be using the things we've used in this video again. So what I'll do is in the next video I will talk about how we can create text files, read text files, and then create binary files and save binary files, all of which basically needed what I've talked about today to be explained first. So thanks for watching. Leave any comments below you have about this video, and I will catch you in the next one. Bye for now.